we will continue with the introductory part of this course. First is because we are talking about innovations in chemical technology, and it would be important to know these terms quite well, because we use these terms a lot. Innovation, invention, research, applied research. Okay, and I mean, when I was looking around, trying to see why, in the first place, why is it called research? Would someone like to suggest why do we call it research? What is research?
We are literally searching for answers, or uh,
Yeah, okay, but why isn't it called search? Why research?
So because it is not completed and at once, we have to do it multiple times. Like
Multiple
multiple
times.
iterations are needed.
Yeah. I think that's nice. Yeah, I think you're right in what you have said. And it is really to look into things that already exist and look into it in more detail. And it's strange, but whatever you actually think of, um, you will actually find that there was something before that. I mean, you are not really the first to entirely think of it afresh. Okay? Even something as profound as Einstein's theory of relativity, they dug out some letters of Einstein. I think about 3 years back, 3 or 4 years back, which earlier people didn't know about, and in that he himself has put down somewhere that actually he drew a lot of inspiration from actually a very famous Scottish philosopher by the name of David Hume. And he had written a book, A Treatise of Human Nature. May have said some things, in a very fuzzy manner, okay? But apparently that triggered something in Einstein. That's what he says. Okay, and one of you has said very correctly, uh, research, because and that's why it's research, because you are actually searching once again, uh, maybe in a slightly different manner, but it's not entirely something that is absolutely in a vacuum. Even the most profound things, there'll be things which were people had debated. Maybe it was wrong, maybe it was a rubbish idea, but it was debated. Okay? And similarly, like you said, the thing is that research is, I would say, it's like a system with a feedback loop. And you always get a feedback, or somebody does, and then you are iterating on that. Okay, and then again there is a feedback, and again you are iterating on that. Okay, and so it's like a spiral, upward spiral of knowledge, which typically happens. Okay, and uh, and research is really about going with a hypothesis, and many times proving or disproving it. Okay, and that's research. I mean, there was a existing hypothesis. Okay, and then you are trying to see whether it is right or wrong, or partially right. Okay, so all of that, and this is the reason for the re part of the research. Now, it's interesting, even something as profound as the original work of Rutherford, when he proposed the structure of the nucleus, and through his experiments on a gold foil, and when he bombarded those with alpha and beta rays, okay, and and then he came to the understanding that it is really a very dense charge, which is present. It's not the original view that it is like a pudding, with everything kind of spread around in an atom. It wasn't that. All of the charge seems to have been concentrated at one point. And it was very profound. I mean, because that was, I think, the first very important breakthrough in understanding the atom. But I happened to read the original paper of Rutherford. Okay, and it's very interesting at the place, towards the end of his this wonderful work which he did. He says, that it is of interest to note that Nagaoka has mathematically considered the properties of a Saturnian atom, which is supposed to consist of a central attracting mass surrounded by rings of rotating electrons. Just amazing. And he showed that such a system was stable if the attractive force was large. And I was just thinking that surely Rutherford would have drawn some inspiration from this past work, in addition to, of course, whatever experiments that he did and he found, and he found a dense central charge. That's what he proposed. Okay, and he could make out because of the backscattering that he found in with the positive radiation. Okay, and so but the point is that he Nagaoka had actually said something like that. So it is not as if there was nothing that Rutherford had to go by. No, it's not true. He must have drawn some inspiration and probably felt a bit more confident in saying what he did, based on what postulate Nagaoka had already proposed. Okay. Now, in fact, it's also very interesting. When I read this Saturnian, um, it also struck me as interesting that Saturn, of course, has many rings. And after all, what did Bohr do? Bohr actually proposed the structure of the atom where you have a central nucleus, the atomic nucleus, and it's surrounded by orbits. And of course, he derived it from the quantization which was already proposed by Max Planck, And but the point is that he showed that there are several orbits, and so electrons will jump from one orbit to the other, and that's again something that Nagaoka said. Nagaoka did not talk about a single ring. He talked about a Saturnian structure, which means that there were multiple such orbits, which he had thought, and that's where the electrons are whirling around. So you can see that even something as profound as what Rutherford and Bohr did, that they did have something to before them, and which certainly would have been some source of inspiration for both of them. Now, it's also very interesting, that from research, we then came to these more advanced terms like basic research, applied research. Okay, and it's interesting that where again these terms, how did they get so popular? Okay, these terms. Maybe the terms existed, but it was not. It was really promoted and popularized by this gentleman, Vannevar Bush. And Bush was the director of the wartime office of scientific research and development in the United States. And they had Roosevelt was the president, and Roosevelt. We were coming towards the end of the war, the World War. Okay, and Roosevelt, uh, almost everyone, if not almost everyone, many of the scientists were engaged in wartime research. And so they were all making, whether it was the atom bomb or whether it was the radar, I mean, all these people were engaged in wartime activity. That was the biggest activity of research. Okay? And so what Roosevelt, he had that farsightedness, and he said, what are we going to do when the war is over? What will happen to all these people? There are thousands and thousands of them. So he asked Vannevar Bush that, can you see what we should do, okay, with this massive infrastructure that we have created, which is serving all our defense requirements. But in peacetime, what will these people do? And Vannevar Bush, he actually wrote, which is considered to be one of the most influential reports. Okay? And it was called Science, the Endless Frontier. Okay? And, it's interesting that in that, Vannevar Bush talks about basic research. And by the way, this influential report, they celebrated it about, I think about a couple of years back, the 75th anniversary of this report, and because it was such an influential report, and all these terms of basic research, etc., became so popular after that. Vannevar Bush was a master strategist. He was in sync with what Roosevelt said, but he was a very shrewd guy. And so what he said is that basic research, and he said that, look, you cannot just say research, it's not all research only. Okay. And he said there is applied research and there is basic research. And what he said is basic research is performed without thought of practical ends. Okay? And because, if you link it up to practical ends, as was the case with all of the wartime research, because they had to produce something. It wasn't all airy-fairy stuff, There had to be something very tangible. And but he said, you don't have to look for something tangible. Okay? What a dramatic departure from the focus that they had, And then what he said is again something very interesting. He said, applied research invariably drives out the pure if the two are mixed. And so what he did was he cushioned a very large number of people, from being held accountable for delivering any tangible results. And so that's what he did, and he did it in a very clever way. And the reason why he wrote that if applied research and basic research are mixed, then it drives out the pure, because that's the truth. I mean, if for example, you are in an industry, a lot of industries will talk about basic research and all, but the truth of the matter is that if you're not really churning out, something very tangible in a reasonable time, they're not interested. And so what happens is that the people who end up, producing products, producing processes, they are the ones who come into the limelight, and these other guys who may be chasing very fundamental aspects, they get thrown into the back burner, and people really didn't take them that seriously, And so, so he basically made this very nice division, and so protected the a very large number of people. Okay? The second, another thing that he said, in terms of basic research, is basic research is the pacemaker of technological progress. If it is appropriately insulated from short circuiting by premature considerations of use, it will prove to be a remote but powerful dynamo of technological progress as applied research and development convert the discoveries of basic science into technological innovations to meet the full range of society's economic, defense, health, and other needs. Okay, and so with that, what he did was that he created a pyramid, and he put basic research right on top, and then said all of these applied research and development is essentially to convert the discoveries emanating from this basic research. Okay, and and then after that, probably then there will be engineers who will develop machines and big plants and things like that. So he created this hierarchy, and it was such an influential report, that here, this is the British chairman of their University Grants Commission in 1957. So almost about 13 years after this report had been published, and you see how influential it is. He writes, "It is obvious that most of the basic secrets of nature have been unraveled by men." Again, remember, these people never, really wrote men and women. They would always write men. Okay, but you can just read them as men and women. Okay, wherever you see this, who were moved simply by intellectual curiosity, who wanted to discover new knowledge for its own sake. The application of the new knowledge usually comes later, often a good deal later. It is also usually achieved by other men with different gifts and different interests. So he reinforced the hierarchy that was created by Vannevar Bush. And in a sense, there was an air of intellectual superiority, okay, about this basic research. That snobbery exists even to this date. Okay. Oh, you'll talk to people. Oh, I work on fundamental research. I do basic research, and basically trying to put themselves high up there in a pedestal. Now, so what did he do? He therefore created a unidirectional model. Okay, this is the unidirectional model, which is the linear model. Okay, and so all of this is basically dependent on this. You do this, after that you do this, after that you do this, after that you do this. Okay, and that's the way they defined it. Okay, and so let's read what it says. The technological sequence consists of basic research, applied research, and development. Basic research charts the course for practical application, eliminates dead ends, and enables the applied scientist and engineer to reach their goal with maximum speed, directness, and economy. Basic research, directed simply towards more complete understanding of nature and its laws, embarks upon the unknown, enlarging the realm of the possible. Applied research concerns itself with the elaboration and application of the known. Its aim is to convert the possible into the actual, to demonstrate the feasibility of scientific or engineering development, to explore alternative routes and methods for achieving practical ends. Okay? Development, the final stages in the technological sequence, is the systematic adaptation of research findings into useful materials, devices, systems, methods, and processes. Okay? And so this is the methodology which was advocated and became ingrained in subsequent generations of scientists. You might think that well, it's quite all right. I felt that it is one of the most destructive reports, and I'll also try and tell you why I think so. And I'm not the only one. Let us look at, and I'll pass on this book to you. It's a book written by someone by the name of Donald Stokes, and I've taken this from that book, Donald Stokes' book. Okay, and it's very interesting that they did a study, and it was really trying to study the life of Louis Pasteur, and they said that, did Louis Pasteur do things the way Vannevar Bush has talked about? And of course, Louis Pasteur existed long before Vannevar Bush. So is it true? Okay. And then this person, James Bryant Conant, in a very famous book, Pasteur's Study of Fermentation. Okay, writes something quite interesting. Okay? And it says, if basic research seeks to extend the area of fundamental understanding, applied research is directed towards some individual or group or societal need or use. This quality is illustrated well by an applied problem from Pasteur's subsequent career, his effort to cope with the persistent difficulties experienced by those who made alcohol from beets. These difficulties led to an industrialist in the Lille region to seek his help. As the dean of the local faculty of science, Pasteur had encouraged his students to do practical work in industry before pursuing industrial careers. So it was something like ICT, the way you go and do your internship, that kind of practical work. Okay. He visited a factory and took samples of the fermenting wheat juice to his laboratory for microscopic examination. Okay? And mind you, Pasteur is doing something absolutely matter of fact, very important for industries which are operating there, who are producing alcohol. Okay? And he went and he said, "Oh, you give me some of your thing and let me see." And then it says, threading his way through a maze of scientific misconceptions, Pasteur identified the microorganisms responsible for fermentation and showed that they could survive without free oxygen. Indeed, that they produce the alcohol resulting from fermentation by wresting oxygen from the sugar molecules in the fermenting juice. In other words, he said this is all about anaerobic fermentation. And remember, ethanol is CH3CH2OH, whereas your sugars are, each carbon has an OH group. So obviously you have to do a defunctionalization of the oxygens. Okay. And so these bugs, which are, of course, they need oxygen to for their metabolism and everything. What they were doing was they were taking that oxygen from the sugar. And so you didn't need to put oxygen. In fact, it was harmful because it was promoting side reactions. Okay. And so he was able, therefore, to really come up with the concept of anaerobic fermentation, and was able to limit so many things. He limited spoilage. He made it more selective. Okay. And so what would you call this? You would say, hey, he took this stuff and he went to his lab and did something. It's like applied research, right? And he said, James Bryant Conant, in his case study of this work by Pasteur, notes that one of the most valuable properties of applied research is reducing the degree of empiricism in a practical art. Okay, the practical art existed; it was there. And what are you doing? It is very empirical. You do this, you do that. People didn't know exactly why they were doing it. Okay, but it's not as if they weren't producing alcohol. Of course they were. But what Pasteur went and did, is that he was able to, through this study, reduce the degree of empiricism in the whole process. Okay, and Pasteur's study dramatically reduced the degree of empiricism in the industries using fermentation. You know? And that is applied research. So Pasteur was, in that sense, really engaged in applied research in at least this kind of work, you know. And we'll go on. Okay, now look at, also this is a little bit as a side, okay, but interesting, because I've seen many people, they talk about, I want to become this and I want to do this and I have this focus, and they're very, very focused. I'm not trying to undermine focus. Focus is important. Okay, but I was just also looking up where did Pasteur get so interested in fermentation and what the microorganisms are doing and things like that. And I chanced upon this particular article. Okay, and what it says is that actually this was after Pasteur had discovered optical activity, and we'll come to that story also. That he had left some ammonium tartrate, okay, in a petri dish. I think, I don't know exactly what study he was trying to do, but he had left some, and he found that, if he, after he came back after some time, okay, and he found that he had left a racemic ammonium tartrate, and then he found that there is some mold, and the mold seemed to have chewed up some of the tartaric acid. And when he analyzed the rest of the tartaric acid, he found that it has become optically active. Okay? And so this bug, had very selectively, this mold had chewed up one of the optical isomers, and it was that that got him very deeply interested in the area of microbiology, and he steadily made a shift, from his original famous work on chirality, towards microbiology, because, and it was a very chance thing, because it happened because this observation that the mold had only chewed up one part of the tartaric acid. Okay, and so you can see that many times, your research can go in a very zigzag manner. Okay, and do not feel scared or sad that you are meandering. Okay, meandering is a very important part of innovation. Okay, and of course we'll be coming more and more into the subject as we go along. Okay, now let me again take you through another example of applied research in that sense, which is basically to reduce the degree of empiricism in a prior art. Okay? Now, all of you, I've already spoken to you about the Haber Bosch process, and you know that Bosch had used an iron catalyst, and which we'll be discussing. We'll be discussing the Bosch part of the Haber Bosch process a little more in detail later on. Okay, and they came up with a wonderful catalyst. Okay, and they were practicing the process, and it became a very big thing, the Haber Bosch process. But the question is, did Bosch understand everything about what there was to know about why the catalyst works? Not at all. They were doing it empirically. They found a good result, presumably from trial and error. Okay, and they also, by manipulations, they improved the catalyst. Okay, and it was a lot later, something like maybe about about 70, 75 years later, or at least 50 years later, that another very famous German, Ertl, okay, he was able to unravel the mechanism by which the catalyst is actually producing ammonia. Okay, and he got the Nobel Prize for it. And but what did Ertl do? He actually reduced the degree of empiricism in a practical art. Practical art was already being practiced by BASF. They were producing large amounts of ammonia, with the iron catalyst. But did they know everything? Not at all. It was Ertl who really helped them to reduce the degree of empiricism in the prior art or in the practical art. Okay. Now, in fact, this is another thing that you'll see me doing a lot, that I will frequently draw on work that my colleagues and I have done over the years. Okay, where it's just to link up with the subject. It's not meant to be unlinked, delinked. Okay, and so I was, and you must always do this. Okay, all of you must always, whenever you're listening to something, you ask yourself, did I do something like this ever? What is the closest thing to this that I've done? Or did I forget about doing? Did I think of something like this ever? And that actually will make it much more lively and vibrant. Okay, you'll enjoy it when you realize that, yeah, I also thought along these things, when I was doing this work for this particular course. Maybe a way you solved a problem or whatever. Okay, now this is, I'd come back from the US in 1984, and then initially I was in a university. I was teaching a course in quantum mechanics, and but then we had to shift to Bombay, and then I joined this industry. Okay, ICI. Okay, and ICI was a very famous industry, which invented polythene, so many other things, and one of the very important products that they were making was the next generation of explosives, after dynamite, which is known as immersion explosives. Okay, and immersion explosives are basically, any explosion actually requires an oxidizer and a fuel. So that's what you are doing. You are and you are just doing a very rapid reaction. Okay, it's an instantaneous reaction, and that's the difference between explosion and a relatively slower reaction. It's not as if the chemistry is different, but it's happening over a very, very short time frame. Okay, and this particular explosive, it is not that ICI really invented the explosive, but they became among the very first, to actually commercially introduce, this particular product. Okay, and even in India, it they introduced it. Okay, now it's a very interesting explosive, because you what it is that there are these droplets. Okay, and these droplets actually contain supersaturated solution of ammonium nitrate. Okay? And the continuous phase in this emulsion is an oil. Okay? Oil and an emulsifier, which is oil soluble, and that helps to form a water in oil emulsion, based on the HLB understandings. Okay, and now what is very interesting is that the volume fraction of the internal phase is something like 90 to 92%. Okay, and the continuous phase is about, by volume, will be about 8 to 10%. What is the maximum volume fraction of a let's say a face centered crystal structure?
74%.
74%. Okay, and it's a very ordered structure. You know that you cannot pack things to more than 74%. The rest is all void. Okay, and so what happened was, I had come back and they gave me a lot of flexibility in what I wanted to do, but I wanted to do something useful. I wanted to do something which the company was engaged in. Okay, And so I said, this looks like a very interesting problem. Such a high volume fraction of internal phase, how is it achieving it? Okay. And, then I started looking at the thing in a microscope, okay, the immersion. And I found that it really achieves it through polydispersity. Okay. So you'll have large droplets. Between the large droplets, there'll be interstices, and then some smaller droplets will get created. Between those small droplets and the large droplets, there'll be again voids where still smaller droplets can be found, and we found these, okay. And so it was possible to explain the packing based on really polydispersity in the first stage. But then I said, what is happening as we continue with the emulsification, because this picture is really at the onset of emulsification when you are starting, and then I found that these mono big droplets are getting comminuted, they're becoming smaller, okay. And it's never monodispersed, but it becomes relatively more monodispersed, and then I said, but if it is getting relatively more monodispersed, and how then is it accommodating this 92% of internal phase, and and then I looked very carefully, okay, and I found that these droplets actually get distorted, okay, from a spherical shape. They become, in fact, some of them we even could identify dodecahedral structures, so they're squished against each other, creating flat surfaces, okay, and that helps them to pack better. Now, that is, what was I trying to do? I was just trying to reduce the degree of empiricism of how these things pack, the droplets pack. Okay? Nothing more than that. Okay. But then, something very interesting happened that this person who was working with me, he did a series of experiments where he kept changing the volume fraction of the continuous phase and the internal phase, okay, and he started making immersions, and what he showed was that when the volume fraction gets higher and higher, the droplets tend to comminute, they become smaller much more easily, and that's what we wanted. We wanted that because the smaller is the droplet, you are actually maximizing the surface area. So when it has a reaction, like let's say I ignite it or I detonate it, what do I need? I need a very high surface area between my internal phase and my oil, okay, so that at in a millisecond time scale it all explodes, okay. And so so we were very interested in making the droplet small, okay. And so he had found this, but as such practically, we knew that we require about 90 to 92% in terms of a stoichiometry, okay. And so, I was actually mentioning this observation of my student to the person who was my boss, in ICI. Okay, and I just told him, it's this interesting observation has been made, that these things tend to comminute very readily, at the as I increase the volume fraction. And then Dr. Roy, he asked me a very innocent question. I mean, we were just chatting, for about 5 minutes. We are just having a chat in my office, and he just said, "So how far can you go?" And what he meant is that how far can you go in terms of the volume fraction? Because the industry required a volume fraction of about 90-92%. And that's all. And he just out of curiosity he asked me how far you can go. Okay? And then something rang a bell. Okay? And I said, what happens if I try to make the emulsion at, let's say, 96% volume fraction. Is it possible to make the emulsion? I found that yes, we can make the emulsion at 96% volume fraction. And the droplets were extremely small, okay? and so it looked interesting. Okay, now at that point, okay, this is the connect between science and innovation. Okay? What happened was that when I found this, okay, I said to myself, what happens if I emulsify at 96%, okay, and just before terminating the emulsification, I put the rest of the oil phase in, so that my final composition is still the 92% or 90%, whatever it was required. And so all I had to do was just put back the oil phase. At the end of the emulsification, it's a continuous phase, so it just adds to the continuous phase. That's it. And with this one little thing, okay, we were able to reduce the time of emulsification, from something like 20 minutes to around 8 minutes or so. Okay, and you can imagine what an impact it then has on the productivity of the plant. The same plant is now churning out 2.5 times more product, okay? Just because of this. Okay, and not only that, another very interesting observation was that when you do the emulsification at the higher volume fraction, the droplets become much more monodispersed, and that's what you want. You want monodispersity because then processes like oswald ripening. How does an emulsion get unstable? Small droplets become bigger. They gradually grow, and then they're gobbled up by the larger drops. But as you make the emulsion more and more monodispersed, that oswald ripening mechanism tends to get fairly eliminated. Okay, and so so what did we do? We actually had there was a product. We wanted to study it, just do basic research. Okay, and really just wanted to ended up reducing the degree of empiricism. And in the process, also something very, very unexpected happened, which was that the comminution rate became so much more better, at the higher volume fractions, and then it led to an improvement in the technology of manufacturing these explosives. Okay, so what can you see? That we were going back and forth, starting with a product. We didn't start with something very fundamental and then made a product out of it. We started with a product, and we wanted to understand that product better. Just like those Lillet people, they wanted to make the fermentation process better. That's it. Okay. Now, so what then is written in the Pasteur's Quadrant by Donald Stokes is something very interesting. The problem of deriving alcohol from beet juice makes this point well. Pasteur's work on this problem is, as Quadrant noted, a distinguished example of applied research, a highly successful effort to improve the technology of fermentation. But the study that Quadrant called a prime example of applied research was at the same time a distinguished example of basic research. Because he came up with something so fundamental, the anaerobic fermentation process, and then much more of an understanding of the mechanism of how exactly oxygen is removed, from the sugars. Okay, this blend characterized virtually the whole of Pasteur's latter career. He probed ever more deeply into the processes of microbiology by accepting applied problems from a Lillet industrialist from the Minister of Agriculture, even from Napoleon. And in a case that did much to build the Pasteur legend, from the distraught mother of a child bitten by a rabid dog. Many of his detailed lines of inquiry, such as the experiments by which he developed the process of the pasteurization of milk, or his experiments in growing attenuated bacterial strains to immunize patients from disease, are unintelligible apart from his applied goals. The only thing in common was he was trying to solve a problem. He had an applied goal. The mature Pasteur never did a study that was not applied, as he laid out a whole new branch of science. How many people can claim to have laid out a branch of science as Pasteur did? But Pasteur did not do it by Vannevar Bush's, dictum that you go ahead and do fundamental research. Out of it will come some great solutions, and out of that will come applied research, and then the technologists will take it forward. Not true. He actually went in the reverse direction. Okay. Now, that brings us to what this book is all about, and the book is known as Pasteur's Quadrant: Basic Science and Technological Innovation, and it's written by Donald Stokes. Okay, and what Stokes did is that he said, let me break up, let me define two axes. Okay? One axis is the quest for fundamental understanding, okay, and the other is consideration of use. Okay, now the people that Vannevar Bush was trying to put in fundamental research, was really this, at the highest so-called level of quest for fundamental understanding, the so-called basic research. Okay, and the other axis is consideration for use. We have seen the considerations for use in some of the examples that I just described to you. Now, one of the people who is put as probably the most famous, in terms of consideration for use, is Edison. Edison actually was not a brilliant researcher. Edison was not certainly a fundamental scientist, and but Edison was unbelievably creative in terms of conceiving products. He could conceive so many different things, not one. And in that sense, probably nobody has surpassed Edison even till today, in terms of the prolific manner. Whether it is the light bulb, whether it is the just phonogram, name it. The number of things that Edison did, or the Edison battery is just incredible. What Edison did. And then what he says, Stokes, is that why why put Edison here? Because Edison actually was a bit loathsome of very fundamental research. In fact, he, sometimes people would say, hey, Edison, what about mathematics or something? And he would say, if I require a mathematician, I'll go and hire the mathematician. I mean, don't ask me to delve into mathematics, And so he was a very practical sort of person. Yeah? Pasteur struck the ideal balance between consideration for use and quest for fundamental understanding. He took a problem. Okay, there was a consideration for use. He first tried to reduce the degree of empiricism, and then he started going beyond, into reaching generalizations which were profound. And that's what Pasteur kept doing. So he is the most famous in terms of use-inspired basic research. And and the second thing is that, everything is not going to flow in the way that Vannevar Bush said, from basic research, going this way. Okay, it could be going the other way. Okay, so but he created this quadrant. Now, just also again as an aside, when I was doing my PhD in Princeton, and it so happens that Donald Stokes was actually in the building literally adjacent to our chemistry department, and I had never heard of him. Okay, and I had no idea. I used to go and eat in that canteen sometimes. But other than that, I had no idea that this person was there. It was only, when I started teaching this course on innovation, and I felt that Pasteur's Quadrant is a very important thing to teach, that I got the book, and then I started reading it. And, I find that first I found out that he is from there, and then I found out that he is also acknowledged my PhD supervisor, and he's also acknowledged Walter Kaufman, who's the person who made the detonator for the atom bomb, and who I used to be his lecture demonstrator, Walter Kaufman's, for the freshman students, and I was thinking to myself, and Donald Stokes is not a scientist, and I said, look at this man, he's consulting so many people, okay, trying to pick their brains, okay, and basically ending up with a very profound book, and now the reason why I'm again telling you this is that the greatest pieces of work will come out of your ability to interact with one another, your ability to test out the ideas and postulates of others, share with others what you think. Okay, like you all are from so many different backgrounds in this course, if you'll come together, who knows what will happen, what you'll create. Okay? It's also very interesting, in 2020 I told Tom Spiro, that by the way, I teach Donald Stokes's book, and I see that you were acknowledged there, and I just wanted some insight from you into Donald Stokes, because he's no more. Donald Stokes has passed away. And then he wrote, I remember when Don Stokes was working on Pasteur's Quadrant, but I hadn't realized that he acknowledged Kaufman and myself. Nice to know. Thought that I'll put it as an aside, that please try and see, if you all can get out of your own areas of expertise, and start interacting. Very, very interesting things might come out of it. In this particular case, what came out is this very famous book. Okay? Now, let me again take you through this book. I said that Donald Stokes himself seems to have forgotten what he was saying, and I said, why has he only in under applied research written about Thomas Edison? That's not true. What did we learn? That applied research is about reducing the degree of empiricism in a practical art. You could be a scientist. You could be doing research. You don't have to necessarily make a product, okay? But you're doing applied research because you're reducing, like Ertl. Okay, yeah, you might say Ertl did fundamental research, but I could also call it as applied research because he was trying to reduce the degree of empiricism in the ammonia catalyst. Okay, so there should be no snobbery, about applied research and basic research. This is as profound as this, and so it's very important. Now, what I also found is that Stokes had kept this quadrant empty. It was empty, and I said, why has Stokes kept this empty? What is this quadrant? Okay? And after all, what is this quadrant saying? it is saying that you are doing something where the quest for fundamental understanding as such is not so high, but you're doing something around understanding. Okay. And also the consideration for use is not so high, but maybe there is some consideration for use. Okay. And then I asked what really therefore would be the kind of work that I would put here. you know. And then I thought that there are so many people who generate data which then other people capitalize on. Okay. And it is their food for thought. If the data did not exist, these people would not be able to do their stuff. They had some data. Then these people over here could be providing some of the supporting evidences that help to strengthen or discard theories. You know, it is. I mean, they're doing. They're doing important work. Or it could be that I'm doing, in terms of applied research, I'm not doing something very, very original. Like if somebody has made, let's say, ethanol from banana peel, and I go and say, hey, there's a lot of oranges in Nagpur and they have a lot of orange peels. Okay, so let me go and make ethanol from orange peels. So I'm working on some variations of a theme. Okay? And then I thought to myself, what do the majority of the people do? Majority of the people, I would say, at least from my experience, at least 99%, if not more, are really working in this quadrant, which has been not even discussed, in his initial part. And so, and yet, this is what we mostly are doing. Most of us are actually doing something around this. Right? So let's not kid ourselves. Everybody is not doing the such a high-end basic research or such a path-breaking innovation or a use-inspired basic research like Pasteur. Yeah? And there's nothing wrong if you're doing this. This is an important quadrant, I found. The problem is if you are not doing any of this, okay, then you are just wasting your time. And you're neither here nor there. Okay. And so I would borrow from Mumbai lingo and say that is time pass research. That's what a lot of people are doing. Okay. It's just, biding their time. Yeah, I'll publish some paper here and there, etc. And you have to ask, did I really make any impact over here? Did I contribute to any fundamental knowledge? Did my work lead to some applied research or a product development or a process development? Did I do it? Or what did I do? And so I'm just saying that be a bit wary. Never get involved in this. Okay? It would be a complete waste of time. I can understand that, sometimes we might be forced to do it. Like if you've got a large number of students and you have to give a lot of students different problems to do, that all of those problems need not be very profound. And so, I can understand some amount of that activity which is related to education. But maybe I'll put it down. It's an idea that came to me. Uh, 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 Things related to education and teaching. Okay, that I can understand, right? But if I'm not doing any of this, then you have to be very, very concerned about what you're doing. Okay? Now, if you have to ask yourself, and this is important that all of you do, you may actually, I find this quadrant useful in also trying to identify what are your strengths, where does your interest lie. Are you or are you interested in all quadrants? There are people who love to do everything. They're brilliant in everything. Okay? And there are some, who will tell you, no, I'm this is not my cup of tea. Something else is my cup of tea. Okay. So where does your interest lie? Okay. And remember, do not fall into the trap of snobbery, of R&D and research and things like that. Okay. Anything that you're doing, okay, which is, in these quadrants or in the top part of this, is important. Okay? There's nothing, don't ever feel that it's inferior or superior, nothing like that. And let me also tell you that many of these people I've seen who so-called are doing basic research, you know, I find that they actually draw on the knowledge of these people, go and do something, and sometimes don't even acknowledge these people. And I mean, okay, they've done some great thing, but let me tell you that the contributions of these people are no less. Okay, so it's important, that you try to look at the Pasteur's quadrant, okay, and ask yourself these two basic questions: what are your strengths, okay, and where does your interest lie? And let's say if your interest lies somewhere, but you find that your strengths are not so good in that, no issue. Go and build up that strength. You don't have to compromise on your interest. Go and develop that strength. Okay, so what you do is that, and this is only an assignment for your own self. You don't have to submit it. Okay, I want you to introspect, okay, and write down for yourself the answers to the above two questions. What are your strengths? Where does your interest lie? Okay, no need to submit it. Now, I mentioned to you about the importance of the bottom left quadrant. Let me show you, some examples, and you can actually decide for yourself who is the greater of the two. And like, for example, take something as fundamental, okay, and as important path breaking as the discovery of chirality. Okay? There are very few things which have been ever done, which are more path breaking than that. Okay? Now, you ask anyone who invented or who discovered chirality, and everybody will say Louis Pasteur. Okay? But let us try and see what happened. It was this person, Mitchellish, who made an observation. Mitchellish was the one who took two different kinds of tartaric acid which were known. Tartaric acid, and they used to call it paratartaric acid, which today we know as racemic tartaric acid. Okay? And he is the one who found out that for whatever, I'm not sure why he did the experiment, what made him do the experiment. Okay? But what he did was that he is the one who found that the action of light, okay, plain polarized light, on these two are very different. Okay, and that one of them rotates the plane of polarization, and the other doesn't. Okay? And it was an experimental observation. Okay? But obviously, it's obviously very, very important. Okay? And why would someone do something like this? Okay? And what did Pasteur do? The moment he found this observation made by Mitchellish, okay, that he did, he obviously had a curiosity, he had that interest to find out, but why did it happen? Okay? Michelish probably stopped with the observation. I am observing this. This did A did this, B did this. And Pasteur would have said, why? And that is still amazing that he put this in a microscope and he was able to separate out these isomers. Let me also tell you that Pasteur was extremely lucky because all racemic compounds don't have discrete negative and positive or plus and minus enantiomers. They could be actually mixed in with the same crystal, in which case I can't take them out. It so happened that this tartaric acid could. It had these as separate, the plus and the minus. Otherwise, he would never have been successful in his experiment. Okay, and so and again, I was also looking at, this is another thing that you must do. First thing I find is nowadays, people will you want to do something and they'll say, but we don't have this instrument, we don't have that thing. How will I do this? And the way these people used to work is, forget about what you don't have. What do you have? Can you do something with what you have? And that's the way you should look at your problems. Don't always think about what you don't have. And after all, what did he have? He probably, what could he have done? He had a solid. He had that paratartaric acid and tartaric acid, and he had a microscope. Okay, and and he had that light source. That for measuring the plane of polarization, and so there was nothing so unusual for him to just put it in the microscope. What else can he do? There are not too many other things that he can do. Okay? So he did whatever he could do, and and then of course his curiosity, that's the number one. And then to have put it in the microscope, really a great thing that he did, and then the patience to sift through these and to take the two out separately. And then, when you can imagine the sense of joy that he felt when he saw that the separated crystals were both optically active and in the opposite direction. And that's when he said basically that everything is found. One of the very, very great things that has ever happened in the area of chemical technology. And today, that how important chirality is, in the area of pharmaceuticals, agrochemicals, so many other areas. Okay? Now, by the way, since I'm talking about chirality, this is the other that I think there is this is too simplistic. And I would put down, in fact, this is again a thought that came to me right now as I was talking to you, that people do not do research just for best for understanding or for making a product. Okay, many times we do things out of sheer curiosity. Okay? It's just curious. I mean, there was no nothing there, which would have told Michelish to do this. It's a curious thing. I probably had a light source, etc. I said, hey, let me see what happens. Okay? I mean, I was not really looking for any quest for understanding. I was just being curious. So, curiosity is extremely important, okay, in whatever you do. let me show you another great example of curiosity, by a person whom you have heard of, our own Dr. J.C. Bose. Okay, and he was working in a college, J.C. Bose. Okay? The same person, who for the first time detected radio waves. Okay, and look what J.C. Bose did, purely with whatever he had, and just because he was curious. He presumably had learnt about all this chirality and the work of Louis Pasteur, and so what he thought is that is it that you have to only have solutions, to have this kind of effect? What would happen in the solid state? Okay? And what he did was he took a bundle of jute fiber, okay? And in one case he twisted it to the right, and in the other case he twisted it to the left. Okay, and he let just like optical light waves, he took electric waves. Okay, and effectively took the polarized electric wave, and passed it through these jute fibers, twisted once to the right and in another case to the left, and he found exactly what Pasteur had found, which was that one bent the electric waves one direction and the other one bent them the other direction, and then he mixed the two, or and he found that there was no rotation of the plane of polarization, and such was the greatness of this work that it was communicated by none other than Lord Rayleigh. That is how famous it was. And say, I hope you can again see, that how important curiosity is in doing things. And again, they never lamented that I wish I was born 120 years later, when everything, such sophisticated instruments existed. They just did whatever they had with them. They just worked with that. So I would strongly advise all of you, please go ahead and do that. Okay. Now coming back to this, you can decide between Mitscherlich and Pasteur, who is the greater. I would put probably both of them at equal footing, because it's so unreal that he did such an experiment as to pass plain polarized light through these things. I mean, Pasteur's half of his work was done by Mitscherlich. So, I would say that he provided great food for thought to Pasteur. It's exactly the same thing in the case of Niels Bohr, and you have seen about Nagaoka, and after all, Balmer, in 1885, long before Niels Bohr, okay, he basically studied the emission from deuterium lamps, and he found these two emissions, okay, and was able to derive an empirical relationship, and he was able to basically explain, okay, the difference in the wavelengths, okay, from this, and we know today that we define one of these terms as the Rydberg constant, and n is your principal quantum number, okay? And so once you know that this kind of discrete values of n, whole numbers, had been worked on, okay, I mean, and also the work of Nagaoka talking about Saturnian orbits, it was nothing so unusual for Bohr to subsequently come up with the structure of the atom. I'm not saying it wasn't great, it was of course very great, but these were great preceding prior art, which must have played in his mind. They must have had a role to play in his entire work. take this again, and again, as I told you, I'll be drawing heavily from my own experience. He is a person with whom I did a postdoctoral research in Brookhaven National Laboratory. Okay, and his name is Norman Sutin, uh, and he is the inventor. Okay, inventor means he is the first person ever, you know, to have been able to measure the rate of an electron transfer reaction. So when we write this reaction, say ferrous plus ceric going to Fe3 plus Ce3 plus, okay, what is the rate of the reaction? Nobody knew the rates of these reactions. And Sutin was basically able to apply. He fabricated this instrument, stop flow apparatus, and he was able to show that this particular reaction occurs in the millisecond time scale. I mean, you could monitor reactions which happen in the second time scale. Okay, but there was no way of monitoring a reaction in the millisecond time scale, and that's the time scale in which these reactions were occurring. And Sutin was the first person to have developed these. Not only that, he also was the first person who developed he found the rate for the self-exchange rate. Like if I take ferrous and ferric, it is not that ferrous remains as ferric and ferric remains as ferrous remains as ferrous and ferric as ferric. There is interconversion between the two. Ferrous is transferring electron to ferric, and ferric is going to ferrous, and again it's going back and forth. And that's the self-exchange rate. Okay, and he generated all these rates, and it's something so fundamental. Okay? And look, where did I learn this from? I learned this from the Nobel lecture of R.A. Marcus. In 1992, he got the Nobel Prize. And he says, one example of the latter was the stop flow apparatus pioneered for inorganic electron transfer reactions by Norman Sutin. It permitted the study of bimolecular reactions in solution in the millisecond time scale. Okay? Now, had Sutin not generated this data, what would Marcus do? He had no data. Okay, it's another matter. It's been argued that why Sutin didn't get the Nobel Prize along with Marcus. But forget about all that. It's not so important. And it's amazing that he had this. Now, this is another important thing that I want you to pick up. That there are some people who have something special. Okay? Sutin had this thing special. He had built a stop flow equipment, with which he could monitor reactions in the millisecond time scale, which till then had never been done. Once I've got something like this, I can apply it to so many areas. Somebody can say, hey, let me go and study electron transfer reactions in organic systems. I can do so many things. It need not be even electron transfer reactions. I can go and study the reactions of simple chemical processes. Some of the processes which occur very fast. So, what do I have? I have an instrument with me. Now, this is another thing that I want you to remember, that when I'm writing what are your strengths, many of you will have something unique. And even if you don't have something unique, try to acquire some kind of a unique skill. It could be that you are a genius in writing software, and and that software could be of great value to many people. Okay, or you could fabricate some instrument which is very special. Okay? Or like Haber, that I had a high pressure apparatus, and therefore I could do reactions in high temperature and high pressure, which nobody else could do. Okay, and we will see how Ertl also generated this reaction mechanism. Ertl had an instrument, had an equipment which nobody else had. You know? So one of the best ways, of inventing or innovating is that acquire a unique skill, something which is special to you. If you have things, and that unique skill could be your brain, you could be having an outstanding brain. Make use of it. Okay, and go and see where all you can use your brain. Okay, so and so this is exactly what these people did. They had an instrument. Now, in fact, I was also asking and thinking to myself that I feel that the way today research journals etc. are uh, published, I don't see anything logical about their structuring. Okay? And I was just thinking that when I looked at some of these great things like Mitchell-ish making an observation, what did he do? He generated some data. What did Sutin do? He generated some data. Okay? And I was just thinking that maybe we should have a journal which is called Journal of Novel Data. And you've generated, and when I say novel, means really novel. I'm not talking about variants of a data. I'm generating that data for the first time. There's no such data existed. Okay, or it could be a journal of novel observations and phenomena like Mitchell-ish. This data would be something more quantitative, like the actual rate of the electron transfer reaction. Whereas this could be that, tartaric acid rotates the plane of polarization of light. And it could be something like this. And there are some people who are not good in generating any data. They're not good in making any observations of their own, but they're very good at explaining things. And so that's this that is what they're good at. So maybe we should have a journal of explanations, and where they can go and look at all these things which people are not able to explain, but for which they have provided data, and they go and explain it. Okay? Like Bohr explaining the data of Balmer. Okay? Or it could be that I'm very good at making a prediction and a conjecture, not completely nonsensical, but obviously there is a basis for making the prediction and conjecture. Let me tell you, I mean, in those days when theory of relativity would have been first, the papers would have come out. Of course, it would have been in the realm of predictions and conjectures, and or you, like Norman Sutain, you could have developed a special tool, and you say Journal of New Methods and Tools, and once I've got this, someone else could pick up the literature and say, hey, this thing exists, I can use it in my work, and then I come to know. Okay, there could be people who are process people and they've invented some absolutely brand new process of making a optically active molecule. Okay, and it could be a journal of new processes, and then there could be other people who would say, oh, I want to make this product, I want to make this compound, I want to make that compound. All of them would now want to try out the journal of new process, and see what they can do with it. There are people who are good at posing problems. They're not necessarily good at solving problems. Okay, but they're good at posing problems. Like we saw in the later part of the 19th century, when the problem was posed, to the scientists, that can you fix nitrogen from the atmosphere? Is what a challenge. Okay. I mean, and that person didn't know how to solve the problem, but that didn't hesitate, or that person didn't hesitate to moot the problem. Or when we'll see when people, the French, the kind of challenge that they posed, which led to the Leblanc process. These are all people who are unbelievably good at posing a problem or a challenge. In fact, let me tell you, it is far more difficult to pose a problem than to solve the problem. It's not easy. Okay. And just look at that. Then in fact there could be some who are very good at inventive problem solving. Some kind of a innovative mindset that they bring to problem solving. Okay? There could be some people who are able to anticipate opportunities. There's not problems. Okay? But they say, I see this as a great opportunity. Okay. And once you have identified, spotted an opportunity, then many people might jump into the bandwagon and they might start working on that opportunity. But it requires huge amount of creativity to identify opportunities. There are also people who are they can look far into the future. Maybe there are people who looked in the 120 years ago, and they said 100 years from now, you have introduced fossil fuel, it's all going to come to an end. Where are you going to get your energy from? And they started working on possible solutions to energy 50 years ago. They're not starting today. They started working long ago. Okay? And they are the people who are able to perceive threats, and do something about those threats. So, I mean, and obviously, when I'm talking about, let's say, chemical technology or chemical engineering, naturally you will sharpen the focus, and you'll talk about obviously novel data in the area of chemical technology. I mean, it's not all embracing and embraces everything. Okay, but it's something that you can keep in mind. To me, it seems that probably a lot more focused solving of problems will happen if things are structured in this manner. Okay. Now, let me now come to we have seen research. Okay, like some of the things that we discussed. Okay, and let us now look at discovery. Okay, because research is not necessarily that I will. It could be research can end up as a discovery. Like for example, Michelish. It's not as if Michelish created an optically active molecule. Michelish only discovered that tartaric acid is optically active and paratartaric acid is racemic. Or even Michelish didn't find out that. Michelish only rotated the plane of polarization, and Pasteur did. Okay, but that was a discovery. They did not actually create optical activity. Okay? Periodic properties of elements, it exists. Periodicity, but it was discovered that elements have this kind of periodic behavior. Okay? That some minerals are radioactive. I mean, Becquerel did not make those things radioactive. He just discovered that some things are radioactive. Well, this is interesting. Real gases, when compressed and rapidly expanded, lead to a drop in temperature. That gases are not ideal gases, that gas molecules can interact with each other, and that you need to do work, to pull them apart, especially when at low temperatures, when they're below their critical temperature. And and that even gases can liquefy. Okay, it's an amazing thing. Obviously there is an element of discovery as well as invention. The discovery is that gas molecules interact. There's no such thing as an ideal gas. Okay, that is the discovery. The invention is putting that discovery to use, and carrying out, let's say, the Joule Thomson effect, and pressurizing the gas, and then expanding it and rapidly cooling it. Okay? Or that the universe is expanding. It is not that we are making the universe expand, okay, but somebody found it out that the universe is expanding. Or that the sun's energy is derived from nuclear fusion of hydrogen. I mean, the sun is burning hydrogen and it's producing vast amounts of energy, and somebody had to discover that. And I'll go through this, by the way, in a bit of detail after this. Yeah? Mars contains substantial amounts of water. That I didn't go and put water there or I invent that, but I discovered it. Somebody was able to discover that. Or that there is something called a gravitational wave, and that it conforms to the what conjectures made by Einstein. I mean, it's amazing that that space is warped. These are all incredible things, which already exist, but someone actually did experiments, measured it. It was the discovery of what was known or what exists in nature. Different parts of the brain have different functions. I mean, what a remarkable thing. Imagine that nobody knew that, and that, there's one portion of the brain which is more into abstraction, another part of the brain which is more into quantification, and so many things. And today you find even in some of these nursery schools, they'll put a picture of a brain, that this part of the brain does this and that part of the brain does that, and how these schools are trying to improve the functioning of your brain. And all the parents are excited about it because everybody wants to see their kids more bright. Or the theory of germs. Germs existed. We didn't create germs. The germs existed, and someone had to figure out that what are germs, and what causes them, and then of course subsequently then how to take care of those germs. I mean, so these are all great examples of discovery. Now, I told you about how does the sun shine, okay, and I thought I'll illustrate it because I don't see really too many things which are more profound than that. Because if the sun did not shine, there would be no life on earth. There would be nothing. Okay? And today, you take it for granted. Sun is shining. Okay? But somebody had to think about these things. How does the sun shine? Okay? And I will pass on this article to you. It's by John Bacall, a very famous physicist. Okay, and extremely lucidly written. Any of you will be able to understand it. And look, it's also important to know that although in a superficial way, in a very hazy way, people knew that the sun plays a profound role on earth. I don't think that was not known at all. But this person, John Herschel, was the one who, for the first time, was able to sort of articulate it in a very structured way. What did Herschel say? The sun's rays are the ultimate source of almost every motion which takes place on the surface of the earth. By its heat are produced all winds. By their vivifying action, life-giving action, vegetables are elaborated from inorganic matter and become in their turn the support of animals and of man, and the source of those great deposits of dynamical efficiency which are laid up for human use in our coal strata. Can you imagine this? It's almost 200 years ago. And the first time was able to bring a much more tangible, structured relationship between the sun and us on earth. Okay? Now, what happened was that after Herschel propounded this, and everybody knew that everything depends on the sun, okay, it became very important to know how old is the sun. Okay, but that's also not the way it started. And it came from the unlikeliest source, this debate. Right? It came from Darwin. Darwin was actually studying, a valley called the Weald. Okay, and he was trying to figure out, how this valley was very rich at one time and it got denuded. Okay, and he was actually building up his ideas for evolution. And because he knew about the work of Herschel, and that all life on Earth obviously depends on the sun shining, as Herschel had said. Okay, so Darwin, did his calculations based on the denudation of the wheel, and he came to the conclusion that for this kind of a denudation of the wheel to have happened, it would have required at least 300 million years. And so, Darwin wrote up somewhere that it will take up 300 million years, and he would have said that probably because Herschel has said that everything on all life on Earth depends on the sun shining. Therefore, it would be reasonable to say that the sun must have been shining for at least 300 years. Okay? And that's what he would have said. He just related his observations on the denudation of the wheel with a very logical thing which Herschel has said. He just connected it up. And what Kelvin said, look, with all the calculations that I have done, I cannot see the sun shining for more than a few million years. I can't remember the exact how many million years, but he said a few million years, and he said, this Darwin is talking utter rubbish in terms of how long the sun must have been shining. Okay? Now, Darwin got so scared, of Lord Kelvin, that in his subsequent editions of his book, Darwin actually removed that controversy about how long the sun has been shining. He just couldn't take the onslaught, of criticism from Kelvin. Okay? But then what happened was in 1928, okay, around 100 years after Herschel, Lord, two things happened before that. Okay? There were One was, of course, Einstein's theory of relativity, and his proposal that there is a mass to energy conversion, and obviously, people knew that that can produce then huge amounts of energy. Okay? That's one. The second was an experiment, done by this physicist Aston. What did Aston show? Aston actually had some way of doing extremely precise measurements, and he was able to measure helium and hydrogen. Effectively, he came to the conclusion that the mass of four hydrogens is more than the mass of helium. Eddington was able to link up what Einstein said and what Aston said, and he then wildly proposed that could it be that the sun is shining because hydrogen is getting converted into helium, which is lighter than hydrogen, so there will be a mass change, and that mass is getting converted into energy and releasing vast amounts of energy. And then, it didn't stop there. He just made that hypothesis, Eddington. Okay? And subsequently, another very great man, Hans Bethe, he was able to write an equation of what exactly must be the nuclear reaction that has to take place for that to happen. Okay, and from that, he was able to propose that this process will release some neutrinos. Okay, and much later, this scientist Raymond Davis did an experiment where he was able to detect neutrinos which clearly had their origin in the sun. And it was all of this work that basically converted a complete conjecture, a hypothesis, into a proof that yes, the sun shines because of nuclear fusion. If you see so much of excitement in the world today because of nuclear fusion, because that is probably one of the most potentially promising sources of limitless energy. It's all because of all this work that enabled us to figure out, that the sun is shining because of nuclear fusion. Nobody, this solution did not fall from the tree. Someone had to work on it. Okay? Now, let me also tell you, okay, that we have gone through discovery, okay, that there's also hypothesis and theory, okay. Now, many times a hypothesis or theory will become a fact when in fact it is proved, like we saw how the sun shines. It was a hypothesis which became a theory. Okay? But there are still many which are still in the realm of a hypothesis. Okay? And nobody is 100% sure whether we have really spoken the last word and nothing else is going to be there henceforth. And in fact, this whole business of what is fact, what is theory, what is hypothesis is written down very well by this person, Stephen Jay Gould, and he's talking about in the context of evolution. And what is evolution? Is it so well known that we are all evolved? And he writes, evolution is a theory. It is also a fact. And facts and theories are different things, not rungs in a hierarchy of increasing certainty. Facts are the world's data. So what Darwin was generating were facts on the denudation of the weed. Theories are structures of ideas that explain and interpret facts. Facts do not go away when scientists debate rival theories to explain them. Einstein's theory of gravity replaced Newton's, but apples did not suspend themselves in midair pending the outcome. Okay? And humans evolved from ape-like ancestors, whether they did so by Darwin's proposed mechanism or by some other yet to be discovered. Okay? And so, he's trying to bring some kind of a connect, between these things. But let us look at things, which are extremely important in terms of debate, and they've not gone away. Like, for example, we know there's a Big Bang and the universe is expanding at present. The question is, will the universe continuously keep expanding, and what happens then? There are some people who believe that the universe will collapse on itself. And so it will expand, go up to a point, and it will collapse. Or, like what is probably the greatest challenge today in to the physicists is what is known as the grand unification theory. Like all these forces, nuclear force, electrostatic force, right? You take gravitational force, they are all so different. And people are trying to figure out, are all these also different, or is there a common origin to these forces? Like we all, we have been brought up with that nothing can travel faster than light. Light is the fastest. But there are people still today doing research, trying to really see, is it true that nothing is faster than light? Nothing can travel faster than light? All the things that we have learned when we were in school, or not, you might have learned in your last years of school or in college, the wave particle duality, that an electron can exist both as a wave and as a particle, and we know that there is an uncertainty in both momentum and in position. Okay, but they've been doing experiments in CERN. Okay, and it's very interesting what they say. The manifestations of wave-like behavior are statistical in nature and always emerge from the collective outcome of many electron events. In the present experiment, some experiment that they did, nothing wave-like is discernible in the arrival of single electrons at the observational plane. It is only after the arrival of perhaps tens of thousands of electrons that a pattern interpretable as wave-like interference emerges. This is very different from believing that a single electron, can be both a wave and a particle. They're saying, no, I mean, we have only seen it act like a particle. And all the wave stuff that we're talking about is all because of an ensemble of many electrons, which we are discussing. This may not be true, what they're saying, but the last word may not have been spoken. Okay? So, it's very, very important that we look at some of these very, very profound questions. Now, in our next class, we will start discussing what are inventions and what are innovations, and then, one by one, we will go into these very, very important innovations that we will be covering in this course. Okay, is it all clear?
Yes, sir.
Yes, sir.